The last part of section 6.3 is volume by washers. Again, it is a solid of revolution, and this solid is formed by having the area between two curves swept around a horizontal or a vertical line, or an area of a single curve that's swept around a horizontal or vertical line that's not the axis, that leaves a gap inside of the solid. I'm just going to give you a couple pictures of things that are going to give us washers and see where the term washer comes from. Let's do y equals x, y equals x squared, and that would be 1 and 1. If I take this region here and revolve it around the x-axis, I would get this region right here. Okay, so this part would be solid, and this part inside here would be hollow. And if I look at an arbitrary cross-section, cut a cross-section out of it right here, that arbitrary cross-section is going to look like this. Okay? And that's where the washer comes from in the title, Volume by Washers, because it looks like a washer from a hardware store where I have a solid region and I have a hollow region. The second way that I can get a volume by washer is if I take a single curve. I'm going to do y equals x, and let's just go to x equals 2. And let's say this around some line here, but the region that's enclosed between my figure and the x-axis. If I revolve this would be what my three-dimensional solid would look like. And again, if I take an arbitrary cross-section, that arbitrary cross-section is going to look like a washer. So what we need to do is we need to figure out how to sum up each of these arbitrary cross-sections. And if you notice, I drew each of the arbitrary cross-sections as a rectangle. And that rectangle, when I revolve it around one of my axes, turns into a circle. So first thing we can think about it is, hey, I can take the area of the big radius and then subtract the area of the little radius, and that would allow me to find the area of each of my base areas. And then if we add up all of these little slices, that will get me the volume of the figure. So let's look at this. So if I take the big area, which is pi big R squared, minus the little area, which is pi little r squared. If I take that and I sum it along my slice area, in this case, and I'm just going to call this the thickness, put th there, and if I sum all of those up from k equals a to b, I will be able to figure that out. Okay, so one thing we can do is we can factor out a pi, and we can turn this into our Riemann sum. And what I'm going to do is, that's going to give me the sum as the limit as it approaches the biggest slice going to 0, or alternatively, the number of slices approaching infinity. K equals 1 to n of pi times big R of x squared minus little r in terms of x squared delta x. And what that's going to give me is the integral from a to b. I'm going to put a pi out in front of big R squared minus little r squared dx, or if I'm revolving around the y-axis or a vertical line, it would be dy. Big thing here to notice that it is the big radius squared minus the little radius squared. It is not the big radius minus the little radius all squared. That is wrong. It's big radius squared minus the little radius squared. So that's the driving factor behind what gives us a volume by washers. And the formula that I'm going to want you to have memorized is this one right here. It's the integral from a to b. Pull a pi out front, or you can put the pi inside. I always pull the pi out front, of the big radius squared minus the little radius squared d whatever for I'm making my slices. So that's the lecture for this section. Now for some example problems.